Welcome back everyone. In this video we are going to study a few characteristics of the elements which are present in the periodic table, and we will also learn how these characteristics vary in this periodic table. In the previous video we have learned that in modern periodic table there are vertical columns which are called as groups, and there are horizontal rows which are called as periods. So we will see that how the characteristics vary when we move from top to bottom in a group or when we move from left to right along a period. Variation of these characteristics are called as trends in the periodic table. So we will be discussing all these characteristics, that is valency, atomic size, metallic, non-metallic character, electronegativity, electron affinity, and the ionization energy. This is our modern periodic table, but we need not learn whole of it. It is too big for us. So we will first of all get rid of these elements which are called as F block elements. We can still shorten the size of the periodic table by removing this part. If we want, we can get rid of the elements of group 2 and group 17 elements as well. Now this much periodic table can be learnt. Basically, what we need to know in class 10 is the elements of period number 1, period number 2, 3 and period number 4 up till calcium. Rest of the periodic table, if we want to learn, it is your choice. Otherwise, you can learn it in higher classes. We will start with the various trends, and our first trend will be for the character of valency. And valency, we know it is the combining capacity of an atom of an element, and it is always equal to the number of electrons lost, gained or shared to achieve the stability in an atom. We will now find out, as we move from top to bottom along a group, how does the valency of the elements change. First of all, we will take the elements of group 1. Lithium, sodium, potassium, rubidium, cesium and francium are the group 1 elements. These are the atomic numbers. Electronic configuration of lithium is 2,1, sodium 2,8,1, potassium 2,8,8,1, rubidium is 2,8,18,8,1. So we see that all these elements have same number of valence electrons, which is 1. If they want to become stable, either they will achieve the duplet or the octet. In both the cases, they need to lose one electron. And losing one electron means they have valency 1. So all elements of group 1 have valency 1. Take the example of group 2 elements. Beryllium has the configuration 2,2, magnesium 2,8,2, calcium 2,8,8,2. All of them have same number of valence electrons, which is 2. And to achieve the stability, these 2 electrons will be lost, which suggests that their valency is 2. So each element has same valency, which is 2. Group 13 elements: boron 2,3, aluminium 2,8,3, gallium 2,8,18,3. So same number of valence electrons which will be lost to achieve the stability. So all the elements have valency 3. We will take one more example of group 17 elements. Fluorine, chlorine, bromine, iodine, these are the elements of group 17. Fluorine has the configuration 2,7, chlorine 2,8,7, bromine 2,8,18,7. All of them have 7 valence electrons. And if these elements want to achieve the stability, they need one more electron to get the octet. So all of them will gain one electron. Therefore, their valency will be 1. Now we can conclude, as we move down a group, all of them have similar electronic configuration and same number of valence electrons. As a result, they all have same valency. Take a note of one more very important concept that we have just learned. All group 1 elements, they have one valence electron. Group 2 elements, all of them have 2 valence electrons. Group 13, 3 valence electrons, and group 17 elements, all of them have 7 valence electrons. Now this concept is going to help us to find the valency of an element only if we know its group number. We will now see the variation of valency when we move from left to right along a period. Elements of period number 2 are lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon, and their atomic numbers are consecutive from 3 to 10. So writing the configuration, lithium has 2 1, beryllium 2 2, 2 3, 2 4, nitrogen has 2 5, oxygen 2 6 and so on. We will see the valence electrons. So these are the valence electrons of all these elements and they vary from 1 to 8 in the consecutive manner. All those elements which have valence electrons 1, 2 or 3, that is lithium, beryllium and boron, they will lose these many electrons to become stable. Therefore, valency of lithium will be 1, beryllium will be 2 and boron will be 3 because it will lose 3 electrons to become stable. Coming to carbon, which has 4 valence electrons, it will share these 4 electrons to become stable, so its valency will be 4. Now nitrogen, oxygen and fluorine with valence electrons 5, 6 and 7, they will gain 1, 2 or 3 electrons to become stable and to achieve the octet. Nitrogen will gain 3 electrons, so its valency will be 3. Oxygen will have valency 2 and fluorine, because it is gaining 1 electron, so its valency will be 1. Neon, which has 8 valence electrons, it is already stable, so its valency will be 0. So now we will see the variation of valency. Valency is first increasing from 1 to 4 and then it starts decreasing again from 4 to 0. We will see the elements of period number 3 also. Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon are period 3 elements with the atomic numbers ranging from 11 to 18 in the consecutive manner. This is the electronic configuration. Sodium, magnesium, aluminium and all these elements, they have 3 shells K, L and M, and this is the electronic configuration. Valence electrons again increase from 1 to 8 in the consecutive manner. So just like period 2 elements, valency of sodium will be 1, magnesium will be 2 and aluminium will be 3 because these are losing these many electrons to become stable. Silicon will have valency 4 and then phosphorus, sulfur and chlorine will gain the electrons to become stable. So again the variation will be valency is first increasing from 1 to 4 and then it starts decreasing from 4 to 0. So we can conclude that along a period when we move from left to right, valence electrons, they increase from 1 to 8 and valency, it first increases from 1 to 4 and then it starts decreasing from 4 to 0. We can note here that all the members of period 2, they will have 2 shells, that will be K shell and L shell. So all the members will have 2 shells. Similarly, all the members of period 3 will have 3 shells each. So now in this periodic table, we can generalize the things that we have just learnt. First thing that we learned is that if we know the group number, we know the number of valence electrons possessed by all the members. All group 1 members will have 1 valence electron. Group 2 members will have 2 valence electrons each. From group number 3 to group number 12, we will not be doing it in class 10, so we are leaving it. Group 13, all the members will have 3 valence electrons. Group 14 will have 4 valence electrons. 15 will have 5, 16 will have 6, 17, 7 and all members of group 18 will have 8 valence electrons. Now we come to periods. If it is period number 1, then they will have just one shell, that is K shell. Period 2 elements will have K and L shells. Period number 3 elements will have 3 shells. Period number 4 will 4 shells. 5 will have 5 shells. 6 will have 6. And period number 7, all the members will have 7 shells each. This information can help us to locate the position of an element if we know its group number or the period number. Let's understand with the help of this example. An element is present in group 16 and period number 3. Identify the element. From group 16, we will know the number of valence electrons, which will be 6. From period number 3, we will come to know the total number of shells it has, which are 3 shells. So K, L and M will be the 3 shells, and M shell, which is the valence shell, will have 6 valence electrons. We know that outer shell can only be filled if inner shells are completely full. So in K shell maximum capacity is of 2 electrons. L shell has the maximum capacity of 8 electrons. So if we count all the electrons, it comes out to be 16, which will be the atomic number of this element. And we know that 16 is the atomic number of sulfur. So we can easily identify the element if we know its group number and the period number. Our next characteristic is the atomic size, also called as atomic radius. It is the distance between the center of the nucleus and the outermost shell, called as the valence shell. So this much distance is called as the atomic radius or the size. Now we will see that how this atomic size vary as we move from top to bottom along a group. We just learned that as we move down a group, a new shell is added with each member. Lithium has just 2 shells. In sodium, one more shell is added. In potassium, there is one extra shell, that is total 4 shells. Rubidium will have 5 shells and cesium will have 6 shells. As the number of shells will increase, the distance of the nucleus from the valence shell will also increase. So the atomic size will increase. In group 13 elements also, boron with 2 shells will have the smaller size because the nucleus is closer to the valence shell. But as more and more shells are added, nucleus becomes farther and farther away from the valence shell. So the atomic size will also increase. Now we can conclude that as we move down a group, number of shells are added, therefore atomic size increases. Atomic size along a period. We have learned that along a period all the members have same number of shells. For example, period 2 elements, they will all have 2 shells each. But that does not mean that all of them will have same size. Their sizes vary and we can understand their variation of the sizes on the basis of the nuclear charge. Nuclear charge is the charge or the positive charge present inside the nucleus due to the protons present in it. If the number of protons is lesser, then lesser nuclear charge is there. If the proton number is more, then nuclear charge will be more. We also need to understand that it is the nuclear charge which is holding the electrons in their orbits or which is attracting the electrons towards itself. In lithium, there are 3 protons or the lesser nuclear charge. These 3 protons are attracting the electrons which are present in the second shell. In beryllium, 4 protons are attracting the electrons from the second shell. In carbon, 6 protons are attracting the electrons from the second shell because all of them have 2 shells each. So as we move towards the right side, nuclear charge is becoming more and more. As a result, force of attraction on the electrons in the second shell is also increasing, thus increasing the pull towards the nucleus. And if the valence shell is pulled towards the nucleus, the size of the atom will decrease. So we can say that as we move from left to right along a period, number of protons or the nuclear charge increases. As a result, pull on the valence electrons will also increase, resulting in the decrease in the size of the atom. Coming to the next characteristic, that is the metallic character. All those elements which have 1, 2 or 3 valence electrons, they will all be metals and they will lose electrons to form the cations or the positive ions, and we call them as electropositive elements. So elements that will be losing electrons will be called as metals. If losing electrons is easy, then metallic character will be more. If losing electrons is difficult, then metallic character of that element will be lesser. This metallic character can be explained on the basis of 2 factors. Number 1 is the atomic size. If the atomic size is more, it means that the distance of nucleus from the valence shell will also be more. As a result, the force of attraction on the valence electrons will be lesser because of the increased distance. So removing this electron will be easier, and easier it is to remove the electrons, more will be the metallic character. So we understand more atomic size means more metallic character. Second factor will be the nuclear charge. So nuclear charge will be due to the protons which are present in the nucleus, and they will exert force of attraction on the valence electrons. And more the force, difficult it will be to remove the electrons. So we understand more nuclear charge means lesser metallic character. Let's see the variation of metallic character as we move down from top to bottom along a group. In a group, as we move down, number of shells keep on adding, means atomic size is increasing. And more the atomic size, farther is the valence shell from the nucleus. As a result, it is easier to lose the electron. Means this element will have the maximum metallic character, while this element, that is lithium, will have the least metallic character, because losing or removing this electron from lithium is very difficult. But removing electron from francium is very easy. So as we move down a group, metallic character will increase. And along a period, because number of shells remain same, but the nuclear charge is varying. Lithium has the minimum nuclear charge and it keeps on increasing. In fluorine, nuclear charge is large. As a result, pull on the valence electrons will also be large, and removing the electrons will become difficult. So from left to right along a period, metallic character will decrease. Now we will see the non-metallic character. All those elements which have 4, 5, 6, 7 or 8 valence electrons, they are all non-metals. If they have 4 valence electrons, they will share these electrons to become stable. If they have 8 valence electrons, they are already stable. But if the valence electrons are 5, 6 or 7, these elements will gain the electrons to become stable, therefore they form negative ions, and they are also called as electronegative elements. The ease with which an element or a non-metal can gain the electrons means it will have more non-metallic character. If gaining electrons is difficult, then non-metallic character will be lesser. So just like metallic character, we can explain non-metallic character on the basis of same 2 points, that is atomic size and nuclear charge. So if atomic size is more, let's take this example. In this case, the valence shell is far away from the nucleus. So gaining more electrons will be very difficult. Here we conclude that more the atomic size, difficult it will be to gain the electrons, so lesser will be the non-metallic character. On the basis of nuclear charge, so let's take this example. Here nuclear charge is more, which means that gaining more electrons is easier. So along a period, all the elements, they have 2 shells. So this one has more nuclear charge, so it can attract more electrons from outside, which means that more the nuclear charge, more will be the non-metallic character. So we see that along a group, because number of shells are being added, gaining electrons becomes more and more difficult. So non-metallic character decreases as we move down a group. But as we move along a period from left to right, nuclear charge is increasing. So gaining electrons becomes more and more easier. Along a period, as we move from left to right, non-metallic character increases. We will now have an overview of the metallic and non-metallic elements in the periodic table. So along a period, we have just seen that metallic character decreases while non-metallic character increases, which means all metals are present towards the left side of the periodic table, while all non-metals, they are present towards the right side of the periodic table. Along a group, we have seen that as we move down a group, metallic character is increasing, which means that all metals are present towards the left side of the periodic table and most metallic elements will be towards the bottom of the left side of the periodic table. While non-metallic character decreases down a group, which means that all non-metals are present towards the right side and most non-metallic elements will be present towards the top of the right side of the periodic table. One more thing we will understand here. We know that metallic oxides are basic in nature. They are the basic oxides. Non-metallic oxides are acidic in nature. If we see the example of period number 3 elements, sodium will form an oxide, sodium oxide, which is metallic oxide. So it will be basic in nature. Magnesium oxide will also be basic in nature. Aluminium oxide will have some properties of the basic, means it will be basic in nature, and it will have slightly acidic properties also. That is, it is amphoteric oxide. Now silicon is a non-metal, so it will form non-metallic oxide which will have acidic properties. Phosphorus oxide will be more acidic, sulfur oxide will be more acidic. So as we move towards the right side, acidic nature of oxides will increase. So we will see that sodium is very strongly basic. Magnesium oxide will be slightly lesser basic than sodium oxide. Aluminum oxide will be amphoteric. Then silicon oxide will be weakly acidic. Phosphorus oxide or phosphorus pentoxide will be more acidic than silicon oxide. Then this will be more acidic, this will be very strongly acidic. So basic character decreases while acidic character increases as we move from left to right along a period. We will now take up a few more characteristics and see their variation in the periodic table. First one is electronegativity, which we will understand with the help of this example of hydrogen chloride. In this molecule, we can see there is one pair of shared electrons which is closer to chlorine. It is so because chlorine is more electronegative than hydrogen, which means that chlorine has the tendency to attract this shared pair of electrons towards itself. And this property is called as electronegativity. So we can say that tendency of an atom inside a molecule to attract the shared pair of electrons towards itself is called as electronegativity. And it depends upon same two factors, atomic size and the nuclear charge. Now see, there are two atoms with smaller atomic size and this one with the bigger atomic size. If the smaller atom has to attract this shared pair of electrons, its nucleus is closer to the shared pair. So it can attract this pair with more force or more effectively. But if this atom has to attract the shared pair of electrons, its nucleus is far away. So the force of attraction will be lesser. As a result, it cannot pull the electrons more towards itself. So we will say that atom with smaller atomic size is more electronegative than the other one. So more the size of the atom, lesser will be the electronegativity. Similarly, on the basis of nuclear charge can also be explained. More the nuclear charge, more will be the force of attraction on the shared pair of electrons. As a result, electronegativity will also be more. Now we can say that along a group, as we move from top to bottom, as the atomic size increases, therefore electronegativity decreases. But along a period, because nuclear charge is increasing as we move from left to right, therefore electronegativity will also increase. Our next character is electron affinity. Whenever we add an electron to an atom, it gets converted into an anion. In this process, it releases energy, and this energy released is called as electron affinity. So we can define electron affinity as the amount of energy released while converting a neutral gaseous atom into a negatively charged ion. And electron affinity can again be explained on the basis of same two factors. First one is atomic size. So electron affinity is the energy released while we are adding electrons. And if we can add the electrons easily, more energy will be released and more will be the electron affinity. So we see in a smaller atomic size, nucleus is closer to the electron that has to be added. So it will be easily added and more energy will be released. But if the size of the atom is more, this electron that has to be added in this atom is far away from the nucleus. So nucleus will exert lesser force on this electron. As a result, it is difficult to add the electron, so lesser energy will be released. So we understand lesser the atomic size, more will be the electron affinity. Now we explain it on the basis of nuclear charge. This atom has a lesser nuclear charge while this one has the more nuclear charge. Adding this electron will be difficult because lesser nuclear charge or lesser force is exerted on it. But here more nuclear charge, more force is exerted on this electron, and adding this one will be easier. So we say that more the nuclear charge, more will be the electron affinity. Now we will see the variation of electron affinity along a group when we move from top to bottom. Because the atomic size is increasing, therefore electron affinity will decrease. Along a period from left to right, nuclear charge is increasing, therefore electron affinity will also increase. Our next and the last characteristic is ionization energy. Just now we have read about electron affinity, that is, whenever we add an electron to an atom, energy is released. But if we want to remove an electron from an atom, we need to provide it with some energy. And this energy that we provide is called as ionization energy. So we can define it as the energy required to remove an electron from an isolated gaseous atom and convert it into a positively charged ion is called as ionization energy. It can again be explained on the basis of same two factors. Now, ionization energy is the energy required to remove an electron. If removing electron is easier, then lesser energy will be required. But if removing the electron is difficult, then we will be needing more ionization energy. So let's see on the basis of atomic size. This atom has a smaller atomic size. This electron that we want to remove is closer to the nucleus. Force of attraction on this electron is more, therefore removing this electron will be difficult. And we need to provide more energy to take out this electron. But if we consider this atom with larger atomic size, the electron is far away from the nucleus and the force of nucleus on this atom will be lesser. And it is easy to remove the electron. So we will be needing lesser energy to remove it. So we conclude that smaller the atomic size, more will be the ionization energy. On the basis of nuclear charge, if there is lesser nuclear charge means lesser force of attraction and removing the electron is easier. More nuclear charge means more force of attraction and removing the electron will be difficult. So we say here that more the nuclear charge, then more will be the ionization energy. Let's see the variation along a group as we move from top to bottom. Because the atomic size is increasing, therefore ionization energy decreases. Along a period from left to right, because nuclear charge is increasing, therefore ionization energy also increase. Now is the time to test our understanding of the various concepts that we have learned. We will start with this question. The atomic numbers of three elements X, Y, Z are 3, 11 and 17 respectively. State giving reason which two elements will show similar chemical properties. We have understood that those elements will have similar chemical properties which have similar outer electronic configuration or same number of valence electrons. So first we will write the electronic configuration of X, Y and Z, and we will find that X and Y both have one valence electron, which means that they will lose this one electron to become stable and they will have similar chemical properties. Go through this question and pause the video and try solving it. Element X has atomic number 13 writes its electronic configuration, which will be 283. State the group and the period to which X belongs. We know that group number is directly related to the number of valence electrons. As it has 3 valence electrons, so its group number will be 13. And period number is related to number of shells present in that atom. So in this case, X has 3 shells. So its period number will also be 3. Is X a metal or a non-metal? Any element will be a metal if it has 1, 2 or 3 valence electrons. Because X has 3 valence electrons, so it will also be a metal. Write the formula of its bromide. We will write X and its valency, which is 3, bromide and its valency 1. Cross the valencies and we get the formula XBr3. I hope you have understood it. We will solve one more question. Choose the elements that belong to same period and same group, and just now we have learned how to find the group and the period. All these elements are provided with their atomic numbers also, so we can write their electronic configurations first of all. We can clearly see that carbon and silicon both have 4 valence electrons. It means that these two will belong to same group, and their group number, I hope you can guess, it will be 14. So only 2 elements will belong to same group number. Now we have to find the elements that belong to same period. For that we will count the number of shells which are present in these elements. Carbon has 2 shells, oxygen 2 and neon 2. So all the 3 elements will belong to same period, and that will be period number 2. While sodium has 3 shells and silicon has also 3 shells, these two will belong to same period, which will be period number 3. You need to solve more such questions to get the clarity, and that is all about this chapter. Thank you so much.